All right, welcome back, everybody. This is another lesson. So this is going to be lesson 2. This is going to be exploring limits a little further. So limits is going to be the main topic of today. So as we know, a limit statement is something written about like this. The limit as x approaches 3 of x is equal to 3. It's just your most basic limit statement. There were a few things I forgot to leave out of the last video that I'm going to talk about now. So the first thing is limits as x approaches infinity. So take this graph. We're going to call this f of x for all intents and purposes. This is f of x. Right? Notice these arrows. These arrows are basically going to tell us the end behavior. This is what we call the end behavior. Now, what is the end behavior, you might ask? The end behavior is the limit as x approaches either plus or minus infinity of the given function. So that's f of x. And that's going to be defined as that end behavior. So for now, we're looking at the end behavior as f of x goes to infinity. That's the first one we're going to look at. And since we see that this is clearly going up forever and ever and ever, it means it is clearly going to infinity. And the limit as f of x approaches as x approaches infinity, as x approaches negative infinity of f of x will be obviously negative infinity. This will differ based on the function that you're given. And there are other functions where it can go to 0. For example, as you can see here, the limit as x approaches, we'll call this g of x. This is g of x. The limit as x approaches infinity, g of x, is going to be equal to infinity. Not infinity, my apologies. This is an example of when it doesn't approach infinity. It's going to approach 0, because this is just going to go to 0 forever. As I will show you, this is going to be just a vertical asymptote, because g of x is actually going to be 1 over x. Right? Well, no, not 1 over x, my apologies. It will be... we'll just call it g of x for now. G of x, there's this asymptote here, this horizontal asymptote. I hope you remember that from whatever previous math class you've taken. There's this horizontal asymptote here at y equals 0. So it will eventually approach 0. Yeah, we can use 1 over x as an example, of course. Let me draw 1 over x really quick. Just give me a sec. So that's about what 1 over x looks like, right? And yeah, the same thing happens with this. The limit as x approaches infinity of this will be going to 0. As it approaches negative infinity, it will also be going to 0. So this is a great function, actually, because we can stick on this for the next topic that I want to talk about, which will be approaching from the left and right sides. So as you can see, there's also a vertical asymptote here at x equals 0, because this function is 1 over x, g of x, 1 over x, as you can clearly tell. And we know that any number divided by 0 cannot and does not exist, meaning the limit as x approaches 0 of g of x Well, I mean, this side is approaching positive infinity. This side is approaching negative infinity, so what's going on? Like, where is it actually going? And the answer is nowhere. This is does not exist. One of the cases of does not exist. This, on the other hand, does exist. Well, it still diverges to infinity, but this is special because this represents 0 from the right side. This is something you need to know. This plus sign does not mean it's a positive number. It doesn't mean anything like that. It means that you're approaching it from the right side. So the limit as x approaches 0 from the right side, I'll write this out, the limit as x approaches 0 from the right. This is incredibly important. That'll be equal to infinity. And the limit as x approaches 0 from the left side, as we can see, it's represented by this minus symbol. It's going to be negative infinity. All right? So that's that. Now we're going to move on to using some of the more tables when we're doing this stuff, because this is largely... Actually, wait, I have one topic I want to talk about. Before that, it's a topic we didn't get to in the first part. It's a topic where the limit as x approaches a certain number c of f of x is not going to be equal to f of c. So we've seen it in functions before, so we'll call this f of x. I hope you're familiar with multiple types of asymptotes, so this is a whole. And this point is going to be 2. We'll call this negative 2, and we'll call this 2 0.5. So we're going to say this is y is equal to 0.5, meaning this will be 2 0.5. So the limit as x approaches 2 of f of x is clearly going to be 0.5. But the limit as x approaches 2 is not actually going to be equal to f of 2, right? It's because we know f of 2 is equal to negative 2. And since negative 2 is not equal to 0.5, the limit as x approaches 2 of f of x is not going to be equal to f of 2. That's a fairly simple concept. Yeah, we're probably going to move on to... now I think we should move on to the more algebraic... we're going to move on to algebraic properties right after we do tables. Okay, so tables are pretty simple, right? Say you have this limit, right? Limit as x approaches infinity of... Not infinity. Infinity is a bad number. We'll choose 5 of 1 over x minus 5. We are going to do a table. So actually, let's choose a different number. Let's do x minus 4. Now we're going to make a table. So we'll do f of x and x. And this is going to be our little table. Now, usually I don't like to draw tables. I usually like to do it in my head. But that doesn't work for everyone. So you have to pick your style. Now, just to clarify, what we're doing here is we're trying to find this limit, right? And we're trying to use this table to find this limit. So yeah. So the first numbers we're going to put in are probably going to be pretty far from it, right? So it's going to be like 0 and 10. And then we're going to get negative 1/4 and we're going to get 1/6, right? Then we'll go 1, 9, then we'll get negative 1/3, and then we'll get 1/5. And then let's go a little closer. We'll go with 3. We'll go with like 5.5 and 6.5. So yeah, we are getting a bit closer, right? So 5.5 will be 1 over 1.5. This will be 1 over 2.5. And then from here, you can about approximate where it's going to go. So you just have to take the middle of these two numbers, which is obviously going to be 1/2. So as you can clearly tell, my apologies, there's a problem here. Clearly a problem on how I did this. Let's see. Yes, I see the problem. Should be 4.5, and this should be 5.5. This should be 0.5. This should be 1.5. So as we can see, when x will be 5, f of x will be 1. And that's how you can easily find this limit. I mean, obviously you could plug it in, but for other functions, you'll see that that will not be possible. But usually you're able to tell, like, the limit as x approaches 5 of 1 over x minus 5, right? As this goes to 4.9999, so as this approaches x from the left, this is obviously going to be a very large negative number, because this is going to be an infinitesimally small number, and 1 divided by an infinitesimally small number, we'll just call this 1s. We'll call s the infinitesimally small number. So 1 over negative s will be negative infinity. Same thing with the positive side, except obviously from the right side, it will end up being 1 over s, that positive small number, which will lead to that infinity. All right, so that's pretty much it for the tables. I went pretty fast in this section. Feel free to go back. Feel free to take a pause. This might be a lot to digest, you know. The tables aren't my favorite technique, but, you know, estimating limit. So basically all we've been doing so far is just estimating these limits, right? Now we're going to actually learn some more concepts about limits, because what we've been doing is we've been practicing and applying what we currently know about limits. So what we do know a lot about limits is that we're trying to find something as a function approaches something. It doesn't always mean that limit as x approaches c of f of x. See, this doesn't, I mean, this statement doesn't always have to be true. So it doesn't always have to be true, right? So what we're thinking of when we're thinking of limits is we're thinking of a number x as it approaches a number, right? But what if we need to do more creative things with limits? What if we get a limit like this? Limit as x approaches infinity of f of x over g of x times h of x over 3. We'll take this. This is, I think, a great use of a lot of different properties that we're going to learn. So the thing we're going to learn about limits is that they're very fluid. So for example, the limit of f of x plus g of x, let's say the limit as x approaches infinity of f of x is some number f. Let's say the limit as x approaches infinity of g of x is going to be g. Limit as x approaches infinity, h of x is going to be some number h. right? This will be equal to f plus g. Reason being, we can split this up, meaning this can be split up into this. So that can lead to f plus g. We can also multiply this. So the limit of g of x is also going to be equal to the limit of f of x times g of x naturally. Let me just write this a little cleaner for you guys. Let me just show you what I mean. So this is going to be f times g, meaning and we know that multiplication and division are just basically the same thing, except they're basically the same thing, right? In nature, they are the same thing. So what you can multiply, you can also divide. Right, so for example, 1 over whatever you're multiplying will be the same as dividing it by that thing. So 1/2 is the same as dividing it by 2. Multiplying it by 1/2 is the same as dividing it by 2. It's just the reciprocal. So for this, what we can do is we can do the limit as x approaches infinity of f of x divided by the limit as x approaches infinity, g of x, as long as this does not go to 0, because that would be very bad, because we cannot we cannot divide a number by 0. Times the limit as x approaches infinity of h of x, and we can divide this all by 3. So what we end up with is f h times 3g. And this is pretty much it, like subtraction, multiplication, division, just the main operators, so plus minus, so addition, subtraction, multiplication, division, right? We're going to have one last thing to talk about, though, which is exponents. So exponents are going to be pretty important. So let's say the limit as x approaches infinity of f of x to the power of 3. We can just take that out. So it's another neat thing you can do with limits is you can just take that exponent out of there. So I'll give you a few practice problems to work this out. So I'll give you the same set, and I just want you to think about everything we've learned so far when doing these practice problems. I'll do one with you, and then you can do one by yourself. So I've done this one with you. I'll do another one with you, and then we can do the rest, and then you can do the rest by yourself. So the limit as x approaches infinity of f of x times g of x over h of x. If you feel like you know the answer, pause and just write your answer in the comments. I'm going to tell you the answer in 5, 4, 3, 2, 1. Okay, so this was pretty obvious. This was fg over h, so f times g over h. I'm going to give you a few more practice problems to do, ranging in difficulty. So the limit as x approaches infinity of f of x times h of x for g of x. The limit as x approaches infinity of f of x times g of x. The limit as x approaches infinity of f of x plus g of x cubed times the square root of h of x. So I want you to do these 3 practice problems. I'll give you the answers in a moment. So I'll give you the answers in 5. I want you to pause. I'll give you the answers in 5, 4, 3, 2, 1. This is obviously going to be f times h divided by g. This will be fg, and this will be f plus g cubed times the square root of h. It's g cubed times the square root of h. All right. That's pretty much everything for today. We will be continuing on limits tomorrow, so have a pleasant day, everybody. And yeah, get ready to learn some more, because I believe we are probably going to go into the squeeze theorem tomorrow. So get ready for that, everybody, and have a pleasant day.